Hello, we are Madfish Solutions, and we came all the way from Ukraine. We are a team of 3 people. I'm Julian, this is Stacy and Sergei, and we are developing Solidity to LIGO transpiler. It's an app which can help you migrate from Solidity to LIGO by translating smart contract and helping you and showing you warnings where it's appropriate. Thank you, guys. I will continue by myself for now, and I wanted to start from the question like how many people here know Solidity? All right, this presentation is directed towards people who know Solidity. It's for total beginners in LIGO. And before I start to go into syntax, I want to tell you about why another smart contract language needs to exist and why Tezos uses it. So Solidity is for sure is not supported in Tezos because of Michelson. It's an underlying language, low-level language of Tezos. In a way, Michelson is Tezos EVM, but not right. LIGO to Michelson is like Solidity to EVM, so LIGO is being compiled to Michelson, and both LIGO and Michelson has some advantages over Solidity. So EVM is low-level virtual machine, and high-level languages like Solidity are being transpiled to EVM assembly language. Michelson is Turing-complete language as well, but it's not a virtual machine. It is more like a separate language which gets interpreted by Tezos virtual machine, and it combines both low-level and high-level features. So on low level, it operates on stack just like Bitcoin or Ethereum, but it has no named variables or functions. And the high-level features include statically typed and purely functional. The language itself is purely functional. And it provides collections like maps, sets, and also it has crypto functions like EVM does, for example, SHA-256 or Blake2B. What does it mean for a language to be purely functional? Pure function is a function where return value is determined only by arguments of the inputs. And pure function doesn't produce any observable side effects. No instruction modifies existing element on the stack, and it only adds or removes elements. Michelson program by itself is a whole pure function, and pure functions have a lot of advantages for common languages, for common programming. Pure functions can be memoized, they can be optimized by compiler effectively, and can lead to greater parallelization. But for smart contracts, the most valuable property is ease of reasoning. So we can have great tools which help us to reason about code because of pure functions. So what is formal verification? Formal verification, it's an act of proving correctness of application with some respect to some specification using mathematics. And the formal verification originated from industries where it needed the most. It is aerospace, medical, nuclear industries, where people's lives are at stake. But in blockchain industry, it is also super useful because we can verify that funds are not stolen, that keys are not transferred, and no funds created out of thin air or destroyed, for example. And unlike usual testing, formal verification is exhaustive. It can prove everything, that the code written is totally according to the specification, but specification may have some errors as well. So it is not 100% guarantee. So how Michelson helps us and how does it compare to EVM? EVM is a virtual machine and it stores low-level code on blockchain. We store low-level code on blockchain on Ethereum. And this code being submitted to the blockchain is extremely difficult to analyze. Solidity compiler by itself doesn't have any certification, so it is also difficult to decompile the code. There are some advancements in this area, like intermediate language named Yule, but Michelson prioritizes verification over efficiency from day one. And you may think like validity maybe is not deal breaker. Solidity and Ethereum exist for a few years, but Tezos' stance on this is that hacks and stolen funds are hurting reputation of Tezos ecosystem as a whole. So Michelson has 2 formally verified implementations, and one in COC and one in F***. And right now, if I'm not mistaken, OCaml version is used on production, and it only has type soundness verified for this implementation. But I think we will have sometime soon a proven version on production. So how Solidity compares to LIGO in that regard? So Solidity is imperative object-oriented language. It's somewhat similar to JavaScript. While LIGO is a functional language, it is influenced by OCaml. And LIGO is intentionally keep tight on features, so it is simple, so there is no subtle complexity. And it is easier to reason about LIGO in total. And it is still Turing-complete language. It is capable of almost everything that can be done in Solidity. Contracts in LIGO can be formally verified, at least on Michelson level. And you have more fine-grained control over logic in LIGO than you have in Solidity. And it's functional if you're into that kind of thing. So yeah, now I want to introduce you LIGO syntax a little bit compared to the Solidity. And it is not different from the Solidity on a basic level. So like math, array access, function calls, it is all present and it's all rather similar. But the paradigm is different. So as I said before, LIGO is functional. And there is OCaml influence. So you have, for example, such quirks like if is always followed by else, and you have to put skip operation if there is no else clause. Or, for example, uint is being called net. It comes from natural. It means natural number, basically unsigned. So somewhat different variable declaration. And you have to enclose your imperative statements into blocks. If someone is familiar with Haskell, it's similar to do notation. And for example, with keyword is something similar to return in Solidity. So I want to show you the function declaration and compare it. All right, so on the top we have Solidity function, as you see, and on the bottom a LIGO function. And as you see, function is the same keyword here. The name is also following the word function. In Solidity, we have types preceding the name of the argument and comma between arguments, and we have modifiers following them, and then we show what we return. And the one statement inside that, you can see we return true. But in LIGO, we have the same keyword function for bar, but then we declare our arguments as const name and then type after colon, and separate arguments by semicolon. And return type is also written after colon. And you will have then block of your code, and with is keyword to show that what you want to return from this function. And as you can see, true word is also written from the uppercase letter. You have similar constructions to mappings and arrays. So you can compare them. You have mapping from address to uint 256 in Solidity, and the same thing in LIGO. But it maps address to net, its natural number. The same thing with arrays is roughly translated like this. You see your in LIGO var nums list, and then you specify type. And after that, you declare your list right in this place. All right, so there is a big difference between how a smart contract is abstracted in both these languages. So in Solidity, basically what you have is your sol file, and you have your contract keyword, which specifies what is a contract. But in LIGO, you have LIGO file, and there should be a special function named main, and this function have to be defined in a specific way. So this is, for example, our declaration of smart contract in Solidity. I think you're all familiar with that. But as this is a scheme of the function which defines a smart contract in LIGO. So you will have to declare your input parameter and current state as an inputs to your main function, and you have to return two arguments. It's a following transaction, so to say, and the new state of your contract. So here is a contract skeleton. This is one function only for this example, and you can see we are accepting two arguments. One argument is input, and the second argument is our previous state. And we are returning two arguments as list of operation and our new state. And here we see declared as types. And after that, after keyword with, we're returning them as values. This thing as a bottom line that nil list of operation basically means empty array. I will explain later in detail what does it mean. So I want to highlight some syntactic differences in these two languages, which I found difficult to understand at a glance when I first started writing in LIGO. So these are tuples, and the declaration or returning them is similar to Solidity or any functional language, but declaration tuple type is a bit different. It's written using the asterisk. As you can see on the second row, you have your foo type, and then asterisks and bar type. And there is an example of returning, and you can see that we define return type as foo type asterisk bar type, but return them using with foo, comma, bar. Right, the next great feature of LIGO that I like, but Solidity doesn't have it in the same way. So it's enumeration called enum. In LIGO it's called variant type, and Christian and Remy talked about it, but I will repeat this as well so you can compare it to Solidity. So it's the simplest case. You can see on the right side that we have an enum coin, and it has a head and a tail. It's two values. In LIGO, this is declared as type coin is, and then you write head and this line and the tail. And if you want to use this enum, you can, in Solidity, you write coin, so it's a type of enum, then name of a variable, and then type of enum dot head. When in LIGO, you write const head, colon, type, and then head without namespace in it. But there is even better usage for this variant type. Solidity doesn't quite have this feature implemented, but I have tried to imagine it. On the right side, you can see some kind of imaginary Solidity. Basically, the idea here is that we can attach a payload to an enum value, and you can see that user is divided to admin, manager, guest, and it has int attached. Let it be ID, for example, ID of this user, and it is attached to the key of the enum. And in the LIGO case, it is a variant type, and it basically wraps this ID around the type. And usage, and once again, it's imaginary usage in Solidity, but let's better focus on LIGO usage. So you declare your user, for example, and the admin, and in the parentheses you write the value, like it's the ID of this specific user. Pattern matching is a way how you use these advanced enums, also called variant types. You write case, and then you specify the key of the case, and this thing in parentheses, you can see to the right side, admin in parentheses ID. Oh, sorry, it's getting translated to the right side, and you can use it at the right side. You can see how for the manager case, I sum ID plus 1000, and that's a neat feature. All right, the next thing is kind of difficult. I will try to explain it to you, but I'm not sure how it will go. But anyway, I hope Stacy will later explain how it works in real cases. But multiple entry points is a difficult case in LIGO. In Solidity, it's pretty simple. So you just find the ABI, you form arguments properly, and you perform the call. There is no much hassle in Solidity for this case. But in LIGO, we have our contract as a singular function. So how do we call another function in this contract? There is a pattern called router, and this pattern leverages this dark magic of variant types and pattern matching to achieve like multiple entry points to our contract. So let's take two functions, for example. I will want you to remember them. It's add and subtract, accepting two arguments and returning like sum or result of subtraction. It's simple. Then for each of these functions, you will have to implement this variant type enclosing int as an argument. And then when you are declaring your main function, you are going to accept both arguments. And then as a return value, you will destructure this argument to get a value out of there and pass it to the function. At the same time, returning a return value of the function that you want to call from the main. You can see at the bottom of my slide, I have last two words. So like you have LIGO dry run main LIGO main. We specify main is the name of contract. Increment in parentheses 5 means that we pass argument 5 as the first argument to our main function named const param of type action, and then we pass the second 5 as a second argument. And if you look to the, I think it's fourth line, you have case param of increment n in bold, and it's get passed to the add function. So as a result, you will get 5 plus 5 in this case. I think it's a bit complicated and it's difficult to explain, but it's a pretty neat feature. It gives you a lot of control and allows you, so as I said earlier, all of this is done to simplify analysis of the contract and allow for easier formal verification, because in Ethereum formal verification is a hard problem, and in Michelson and LIGO as well, it is kind of solves problem, but I think it's a lot of work has to be done on that field. And on the good news, so since we are writing Solidity to LIGO transpiler, we are able to generate a router based on your Solidity code. And but you may have to specify more concretely what your function does, what is the visibility, what are the specifiers like pure view internal, so our transpiler can better understand if the function should be put to router or if it is just internal function that has to return only one value. So yeah, and also we have been working with LIGO for past 3 months, and everything was improving thanks to LIGO team, so it's getting simpler and simpler every day. Yeah, for the next part, I want to invite my colleague Stacy to tell you about atomic swaps. We have a real-world contract transpiled using our Sol2LIGO utility, and Stacy will highlight you the best parts of that and explain how it works. Thank you.
Yeah. Hi again. Let's look at our compiler in action. We prepared a real-world example that is an atomic swap. It's a smart contract that enables exchanges from one currency to another one without using any third parties or middleware. It is a really awesome example as it contains a variety of types, functions with different mutability, structures, and enumerations. Let's start with structures. We need structure swap, which contains information about exact swap. Time lock is time until the swap, until the value is locked on this contract. As a trader is someone who sends this money. Withdrawal trader, the guy who receives this money. Secret lock is a hash of secret key, and that one who provides the secret key will receive money. So. In compiled version, we receive type records that has all fields from the original contract with transpiled types. That means the unit becomes not, addresses remains addresses, and bytes with different lengths becomes bytes. Solidity has such a thing like default values. And when you declare a variable without setting its value, it gets a default value. So for structures, we need in LIGO define this default value by setting each of its fields to our imagined default values. There is such a thing in Solidity like enums that were told by Julian. And we compiled in a bit different way, not using variants. We declare constant for each subtype of the enumeration. And the default value is the 0, 1. Both LIGO and Solidity contracts has states. In our case, we have swaps and swap states. It is a mappings of structures, and in a compiled version, we wraps it all in records, and that contains fields that inherits names from the original contract. We do not have events in LIGO, so we just comment it out with its names and arguments, and then developer can use this information to remove it or to change it to something else. Also, LIGO doesn't have modifiers, but we dispatch body of modifiers in functions directly, and modifiers declaration we just comment. That is the most interesting part of my speech. It is for function transpilation. You can see that the function open. It has some arguments and it returns nothing. Also, it is public payable function that has one modifier. The first line of our transpiled code is part of modifier, and then the body of the function goes. You can see that the function returns two values, operation list and modified state. And it has an extra argument, state. As it is another kind of function, it is a view function that returns some values. By this reason, we need to pass an extra argument to our function, that is receiver contract. And in the last line of the function, we create an operation that sends all these values to that contract. And our function returns only op list because it shouldn't modify state. Another function, close function, it is a function that modifies state and interacts with other contract or other user. That means we have a transfer operation in our contract, and by this reason we should create a list with operation that sends money to withdrawal. And also we should modify state, as you can see we do. Another view function. In LIGO it has not much sense because you can get value from state directly, but in Solidity you can't derive structure from mapping and get its field. So you have transpiled version on the right side. Another function is expire. It's quite similar to close function, and the most interesting part is probably default values. Also, it was mentioned 2 times today that LIGO has only one entry point, that is main, and we should dispatch functions somehow inside of this main. For this purpose, we need such an argument as that has a router type, and it is declaration over this type, and we pass it to the main and dispatch its arguments to the functions. All right, but we received a compiled contract, but LIGO and Solidity are very different, so manual fixes are inevitable. Here you can see we retrieve structure from mapping, and it's too complicated for LIGO, so we should split it to few operations. And one more time, but in a different context, and one more time. And now we have fully compiled code. It is compiled code in very understandable Michelson. You can use it, test it, whatever you want. And to sum up, we have two stuff. It is a CLI version and web version. And probably Julian will show web version.
You have, yes, 10 minutes?
10 minutes, all right. So I think we can show you the web version.
Microphone.
We don't have a wide team, unfortunately. Huh? Yeah, so we don't have a wide team, unfortunately, but I'll just quick introduction. So on the left side, you have your Solidity code. On the right side, you have a Pascal LIGO. Yeah, I haven't mentioned we are transpiling to Pascal LIGO dialect. And if you have some errors, they are going to be on this tab. I'm not sure if it's visible on the screen. So yeah, it's pretty simple to use. We will share the link. You have a few examples here, starting from the simplest, and then go into the real world examples. For example, you have while here, and you can see how, for example, while is getting transpiled here to LIGO while, and like how this. Let me make it even larger. So how these constructions are getting transpiled. So these not equals transpiled to these. And that LIGO doesn't have increment assignment, and we have to emulate it. It's not clear, but roughly the same. And if we have a return value, we return it. Yeah, so I encourage you to try it. And also the contract which Stacy told you about is an atomic swap. We have it in examples. So it's a real-world atomic swap. It works. In Solidity, it works for sure. But in LIGO, after a few fixes, it works as well. And we didn't try to do atomic swap exactly, but we checked it. And after a few fixes, you can try it as well. Yeah, I think that's it. I want to invite my colleagues for Q&A if you have any questions.
Sure, thanks a lot. Yes, questions.
What is the most used LIGO language? Pascal LIGO or Reason LIGO? Or the most used?
I'm not sure. When we started from when Pascal LIGO was, I think, is the only variant, and Camel LIGO was not as developed. But right now, I'm not sure.
That might be a question to the LIGO team.
Yeah, it is.
We don't really know.
Okay.
We have some feedback. Okay, we do have feedback from some people who tried one or other variant, but we don't know how many of them are using such and such variant.
Okay. So your transpiler is transpiled in Pascal LIGO, right?
Yeah, it is to Pascal LIGO right
Thank
now.
you.
I think it's because it's the most friendly. It is the most similar to Solidity. That's the reason.
May I? Because I mentioned that in my own talk, that we are going to do transpilation between different front ends of LIGO. So you won't be stuck in Pascal LIGO if you don't like it. So their work is going to be reusable in Camel LIGO or Reason LIGO or whatever front end comes next.
Okay, thank you.
Thank you. Other questions? Nope. Well, thanks again to the Madfish Solutions team.